Our method for solving separable differential equations relies on computing two integrals. As we've seen in calculus, some integrals are easier to compute than others. In this next example, we'll need to work a little harder to compute one of the integrals. Let's find solutions to the differential equation dv dx equals v squared plus 3v plus 2 over x. To see that this is separable, we can divide both sides by v squared plus 3v plus 2 to get 1 over v squared plus 3v plus 2 times dv dx equals 1 over x. And now that everything with v is on the left-hand side and everything with x is on the right-hand side, we can integrate both sides with respect to x, giving the integral of 1 over v squared plus 3v plus 2 times dv dx on the left is equal to the integral of 1 over x dx on the right, where that right-hand integral is the natural log of the absolute value of x plus a constant c. And the left-hand side can be simplified using the substitution rule as the integral of 1 over v squared plus 3v plus 2 dv. Now, the left-hand side is more difficult to integrate than the right-hand side was. To integrate it, we need to split the denominator 1 over v squared plus 3v plus 2, which can be factored as 1 over v plus 1 times v plus 2, using partial fractions. If you'd like to see these steps done out, you can click on the pink link here. Separating 1 over v squared plus 3v plus 2 into partial fractions gives 1 over v plus 1 minus 1 over v plus 2. And with this partial fraction decomposition, we can now compute the integral 1 over v squared plus 3v plus 2 dv as the integral of 1 over v plus 1 minus the integral of 1 over v plus 2, which is the natural log of absolute value v plus 1 minus the natural log of absolute value v plus 2, which can be simplified as the natural log of v plus 1 over v plus 2. And thus, combining this with the integral from the right-hand side, we get that the natural log of v plus 1 over v plus 2 is equal to the natural log of x plus c. This is an implicit solution for our differential equation that we can solve explicitly doing a little bit of algebra. To solve this explicitly for v, we want to start by exponentiating both sides. On the left, we'll get v plus 1 over v plus 2. On the right, we'll get plus or minus e to the c times x. And we can replace plus or minus e to the c with k as we did before. So this gives us that v plus 1 over v plus 2 is equal to k times x. And to continue solving for v, we'll multiply by v plus 2 on both sides to get v plus 1 is equal to k times x times v plus 2, which can be distributed to give us k times x times v plus 2 times k times x. And now moving everything with v to one side and everything without v to the other side, we'll subtract 1 and subtract kvx from both sides to get v minus kxv is equal to 2kx minus 1. On the left, we can factor out v to get 1 minus kx times v, and finally divide by 1 minus kx to give our explicit solution, v equals 2kx minus 1 over 1 minus kx. As we said at the start of this video, we had to work harder at this example because the integral presented to us was more difficult to solve and required a partial fraction decomposition in order to compute it. So as stated earlier, these separable differential equation problems will vary in difficulty based on the difficulty of the integrals that arise.